Recording. Okay, welcome again. We have 99 students. That's really great number. I hope we can keep that number on during the entire semester. By the way, if you don't know me, I am Ismail Uyanık. I am also working in control theory, just like Şölen Hoca. So this is for this month. I think I can't really guess how long it will take, but we will be together for this course. So during these times, we will be talking about capacitance, inductance, and then we will be talking about response of first order RL and RC circuits. So RL is resistance and inductance, and RC is resistance and capacitance. So we will be talking about those response of those type of first order circuits, and then we will have another quiz. Then Şölen Hoca will be continuing for the next part of this course. Let me open my notes here. Okay, so I will share my screen. So anytime during the lecture, please do not hesitate to interrupt. That is very important for me. So we need to be talking as much as we can. And whenever you have a question, just stop right there. I can't really follow chat message. So if you have any questions, please do turn on your microphone and try to talk. But I will try to check chat as well. It may not be that frequently. So if you think I am missing your question, just stop me. Okay, so today's topic will be about inductance and capacitance. So let me just write the chapter name here so that you can follow what we are going to talk about. So up to now, you learned some circuit analysis techniques, like you learn topology, you learn node voltage equations, you learn mesh current equations from your previous classes as well. So you should be a master of those topics already. I really want you to practice those concepts, because we will be building on those concepts in the next topics, and then it will get more and more complex. So if you solve any issues about those topics now, that will be very helpful for your success in this class. So one nice thing I need to say is all those analysis techniques, especially those simple node voltage and mesh current analysis techniques, will be directly applicable to circuits with inductors and capacitors. So up to now, like most of the circuits you were dealing with had only resistances, like sources, of course, but mainly the components that we were dealing with was resistance. And then we were relying on Ohm's law. Everything was easy. Actually, everything will still be very easy for you, but we will just add different components, and we will try to analyze their behaviors as a part of a circuit, complex circuit. So for this course, I think we will be talking mostly about inductors. If we have time, we will also switch to capacitors. So that will depend on how much time we have. There is one thing common that we should first talk. These are passive components. So passive means in terms of electricity, you cannot generate electricity with these components, so you cannot generate any power. But one nice thing about these inductors or capacitors, unlike the resistors, they can store energy. For example, when you have some energy in the circuit, you can store them on an inductor or on a capacitor. Then whenever you need, you can take them back, so that like, you can temporarily put your energy into these components, unlike the resistors where you can't really do this. They will just dissipate the energy. So you can store them inside like capacitors, and then you can take it back whenever you need for another task. So that is something very very important, and we will be relying on this concept a lot, especially in your next courses in this department. You will be relying on these concepts a lot, that storing energy in these components. So let's just start with an inductor. I hope you can clearly see the node screen. So inductors, just I can just plot a circuit symbol for an inductor. So this is how we represent an inductor. This is just a component that you will be placing somewhere inside your circuit. So that will depend on how you want to build your circuit. So for inductors, we generally represent them with L. So this is the very common symbol for an inductor. This is a global notation, so please try to rely on this notation as much as you can. Again, just like resistors, there will be a voltage drop across the terminals of these inductors. And again, as I said, we will be relying on terminal behavior on these components. And then, of course, there will be some current passing through this inductor. Actually, it will depend. We will talk about this. So when they won't allow any current to pass. So this is a very simple but general description of how an inductor will look like. And then when you had the resistors in this scenario, for example, we were representing them with the letter R, right? And then we had the unit for the resistance of that resistor. So that was ohms. Does anyone know the unit for an inductance?
Henry, I think.
Henry.
Yep. So this is the name of the guy who invented this. So the unit for inductance is Henry. So we will generally say like 3 Henrys, 2 microhenries, 5 millihenries. So you will be hearing this unit a lot. So that is the unit of inductance, the amount of inductance for this component, let's say. So and for the other things, of course, you know the units. So for the voltage, we know this is volts, right? And then for this current, we know the unit is amperes. And then we have time, of course, there will be a relation, time relation. So that will be seconds. And then I don't know if we missed anything, but I think that should be all. So in the case of resistors, we had a unique relationship which describe current voltage relationship between, not between current voltage relationship of a resistors. Right? We were calling that thing as Ohm's law. So we were saying there's a very nice, for let's say for a resistor, oops, for a resistor, we had this very nice voltage current relationship, right? So now we really need to generate a similar, say a similar relationship for voltage and currents of an inductor. So this is not as simple as in the case of resistors, but of course it's not really a big issue. So in the case of an inductor, the voltage current relationship will be written as V equals L times EI over dt. So here you can see the way your current affect your voltage drop on this component depends on the rate of change in the current. It's not directly depends on the current itself, the magnitude of the current, but it depends on the change on the current. So if you try to focus on this equation, you can imagine like the intuitional functionality of this inductor. So since like you're only having a voltage drop here when there is a change in the current, right? So basically, I can simply say that if there's a constant current, so let's say if I am applying a constant current, what is the voltage going to be?
Nothing, 0.
Yes, exactly. So if there's a constant current, its derivative will be 0. There is no change. And then basically the voltage across the terminals of this inductor will be 0, which means that this inductor will be short-circuited, right? So this is how you can understand how this component will react to the changes in your circuit, to the changes in the current or voltage in the circuit you are working on. So that is something very important, and of course, at the same time, like this is like, if you again focus on this equation here, this is like the voltage drop will occur here based on the magnitude of this magnitude of the change of current here. So it's like you will be having a component here which will try to resist changes in the current. So it's like it's trying to stabilize the changes in the current, because based on that change, it will create a voltage drop here, right? So that is something very important. And then this equation also brings something very important, which is you cannot have an instant change in the current, right? So imagine, let's say, imagine an instant change in current. So it's like you, it's not physically possible, but imagine you suddenly change the current from 2 amperes to 5 amperes. What is going to happen? So you have a switch, you just, like, let's say, you just double the current flowing through the terminals of the inductor. So can you guess what is going to happen?
Voltage drops, maybe.
Like, okay, like look at this equation. And then imagine you're doubling the current instantaneously.
High voltage maybe. Or
Yes, there will be extremely high voltage. And actually, if you're trying to write this mathematically, so an instant change here means that this will be infinity, right? So that derivative will be infinity because there's an instant change in basically zero amount of time. So in that case, so this will be, well, let's say, it's better to write this in this way. Let's say instant change here. So that will yield infinity, an infinite voltage here, which is not really possible. So basically, if you try to instantaneously change the current, this inductor will resist to it by creating an infinite voltage drop. Basically, it will be like an open circuit component here, which will not allow the current to pass. So it's like, it won't allow that instant change to happen. So it's like, it will filter this. We will later see the characteristics of these components, I think in ELE 220 course, but for now, what we should know is if you are trying to apply a constant current, then this will behave like a short circuit. Like there will be no voltage drop across the terms of the inductor. That current will directly pass through the terms of the inductor. But if you're applying if you're trying to apply an instant change in the current, that won't be possible because the inductor will block it. Because mathematically that will correspond to infinite voltage, which was not really possible in our theoretical analysis. But you should remember something. This is not possible in a physical system. Like you cannot make a current, change the current from 2 amperes to 4 amperes instantaneously. So there should be a tiny bit, even if it's like tiny bit amount of time, where this derivative will be a number, like a non-infinite number, like a finite number, let's say. So, but of course, that number will be very huge. There will be a huge voltage spike, which is not again possible. But so we should say that this is not something we can physically implement. But of course, we can make that duration extremely small so that we'll be having a finite but huge voltage change. Right? Okay, so this is the very basics of input-output relationship or current voltage relationship of an inductor. Let's just work on a very simple example so that we can try to understand this this current voltage relationship. So I will be just trying to plot this graph of I think this is a graph of a current across the terminals of an inductor so that we can try to calculate the voltage drop across time given this curve. So that is, I'm trying to plot this axis as fast as I can. Okay. Okay, and then let's say this is 1, this is -1, this is 0, this is 1, 2, 3. I hope it's equisampled. And then we have time here. This is time axis, which is in the units of seconds. And this is our this y-axis is our current. This is with the units of amperes. So let's say this is the current profile we are applying to this inductor. So that goes all constant all the way until 2, and then it drops back to 3. So imagine this is the current function of current with respect to time for an inductor. And then let's say this inductor is 3 Henries. Can someone help me to plot what the voltage graph will look like? So by the way, I should write this equation also here so that we can remember the relationship between the current and voltage. Is there any volunteer that can help me to plot this? So I will just try to put this graph like lines here so that we can use it when we are trying to plot. Okay, now I need a volunteer.
I can help you maybe.
Of course. Can you say your name, by the way?
My name is Emirhan.
Emirhan. Okay, Emirhan. Okay, so for this one, what I would like you to do is to look at this graph for like we have different sections here where the current has different characteristics. So we should analyze this part by part, like region by region. So can we start maybe from this -1 to 0? So what this how the voltage will look like in this region?
There is a positive change, so di per dt is equal to, I think, 1. So the voltage is 3H time 1 and 3 volt.
Okay, so you're saying from -1 to 0, di over dt is 1. So basically in this region, the voltage is 3 times 1, that is 3 volts, right?
Yes.
So you're saying the voltage will be constant here.
Yes, I think.
Okay, so let's say this is 3 volts. So what Emirhan is saying, if I take the derivative of this current graph here in this region from this -1 to 0, so it has a constant slope. So its derivative is positive because it's going from 0 to +1 in 1 second. So it's like the change is 1 amperes, duration is 1 second, so that will be 0. That will be 1. And then if I multiply it with the inductance, which is 3 Henries, so we will be having this constant voltage line here, right? Okay, Imran, what is going to happen next?
From 0, we don't have a change in the current, so there is no voltage, I think. From 0 to 2 seconds.
Perfect. So from 0 to 2 seconds, Imran is saying di over dt will be 0. Basically, P will be 0, right? Because there is no change in the current. So let me do this so we can see the graph. So we will move here, and then I will be saying there will be no voltage from 0 to 2 seconds, right? Perfect. And then what happens? In the last 1 second, from 2 seconds to 1 second.
And then we have a negative change in the current, so I think we have negative current, a negative 3 volt.
Okay, so from 2 to 3, di over dt is -1. So basically, voltage is 3 times -1, which is -3 volts, right? So here in that case, we will be having a constant -3 volt change here. So what's the -3 volt voltage here, right? So let's also label it right here. So that would be minus 3 volts. And I move this here so that if I share these notes, you can see them on the same page. Okay. So thank you, Imran, by the way. So if you look at this graph now, like this is really simple to generate. You know, I believe that all of you can easily generate these kind of graphs. Like when you see this current plot, you can immediately draw the voltage plot. But you should just calculate the current voltage relationship one by one for each region, and then you will plot them. It's extremely simple. But there is one thing I want you to notice here. It's some nice feature. So we said, I think somewhere here, you cannot have an instant change in current, right? Like this is not really possible because you will be having an infinite voltage. But if you look at this plot, although we cannot have an instant change in current, we have instant jumps in voltage, right? So you should always remember this. So in an inductance, although you cannot change the current instantly, you can change the voltage instantly. Basically, again, those instantly terms are not like a little bit vague, but you should theoretically understand the difference between the instant change in current and non-availability of an instant change in current. But you will be observing an instant change in the voltage, right? But this is something I really want you to focus on for now. Okay, so let's continue from this topic. So up to now, what we said, so we wrote this beautiful relationship. So we said the voltage current relationship is V equals L times di over dt, right? But if you look at this equation, so it's like it assumes that basically we have the current, so we can take its derivative, multiply with inductance, and we can calculate the voltage. But what if we have the voltage and we are asked to calculate the current? So this equation will not be directly useful in this form to do this reverse calculation. So we should play with this equation a little bit so that we can find like basically an analogous inverse equation that will allow us to calculate current given the voltage, right? So let's try to play with this equation a little bit as much as we can. I will try to work as clearly as possible, but again, if you feel uncomfortable with any steps, just stop me. We will discuss. So first of all, I will make a change here. So I will say. Like just for notation, we were dropping t's, but I think it's time to put them back here. So what I only did is I added this t's times here because that voltage and current depends on time. Actually, that is also the case here, like everywhere. So like the graph of this current and voltage depends on the time. So these were time axes, right? So now I just plug in back those variables so that we understand that when you're taking derivatives or integrals, those t's are meaningful because you should know which parameters your variables depend on, right? So in this case, what I'm going to do is I will multiply both sides with dt just to simplify the equation. So I will say if you multiply both sides with dt, so let's say multiply both sides with dt. So what we get is Vt times dt equals to L times di over dit, right? So basically that is a very simple. That's a very simple case. So in this scenario, now I will take integrals for both sides. So this like this t will not be meaningful here, but you should know that this current depends on integral, but the parameter of this integration component, like this di, that thing will depend on I itself. So if you're trying to take, for example, derivative with respect to time, so you should apply something like a chain rule. You will be taking derivative with respect to current and then taking derivative with respect to t. But for now, for our equation, this will depend on di itself only. So now what I'm going to do is I will take integral, but oops, sorry, but this integral will depend on dt here. So basically it will depend on time here, and then it will depend on current here on the right hand side. But of course, I know that current also depends on time. So based on the analysis we are dealing with, we may need to modify this a little bit. So now what I need to do is I will make some changes in this equation so that I can include the bounds for this integral. So we should decide where we are going to start. Like for example, this side, or for the left-hand side, this depends on t. So we should define the initial time, and we should define the final time where we're trying to calculate. So basically the initial time can be anything, like I can just say t0. So this is just an unknown number. So we will start from t0, whatever that t0 is. Generally, typically, let's say it's 0. T0 is so basically like you start the time from 0 seconds. But we can keep this parametric. We can just say the lower bound of this integral will start from t0. For the upper bound, I can just say t. So I don't need to calculate this until a specific numeric time. I can make it parametric. I can just say t. So whatever time you want, you can just plug it in and calculate your result. But of course, when I put, so let's say, when I put t0 and t here, I don't want this dt to be confused with my with this t here that I am trying to calculate up to that t. So I will be replacing these t's here with maybe vy. So I will just rename those variables because they're just the parameters of this integration. It really doesn't matter at all. So I will be taking this integral of this vy dy, and then I will be calculating it from t0 to t, right? And then for the right-hand side, so that L doesn't depend on anything, so I can just take that directly out. And then here, this side of this equation, now this integral depends on current. So I should define the initial and final values in terms of this current. So it's like we said for the left-hand side, the time will start from t0. So basically, I should say I will be using the value of the current at t is equal to t0. And then I will calculate this up to I of t, basically the current at t0. But again, I don't want to confuse myself with using the same symbol I for the bound and the integration parameter itself. So I will just change this with dx. So whatever the result of the integral, I will be plugging in these bounds. And I know from your math classes, you're an expert on this type of simple integrations. You can do them extremely fast whenever you have the problem itself, right? Okay, so let's now try to calculate the result, right? So for this part, it's not really directly obvious because we don't know the like for this left side, we don't know what this Vy is going to look like. So we will be having a function of time for the voltage that can be just like these graphs that we had before, right? So this is a little bit ambiguous for now. We can't directly calculate this integral, so I will leave this integral as is. I will just say, whenever we have that voltage equation, we can calculate that integral. But if you look at the right-hand side, it's just dx. There's no function here. I can just take the integral of dx, which is going to be x. It's that simple. So for this side, as I said, I will be I can just swap the sides. That will be more easier for me. So the integral of dx is x, and I will be evaluating that at it and it0, right? So that will be equal to integral from t0 to t vy dy. And then I can calculate this left-hand side again. I can say L times, I can first actually take this L to the left-hand side. right? So I can divide everywhere with L. So that will be 1 over L. And then I can say the left-hand side will be IT minus IT0 equals 1 over L times T0 T Vy dy, right? And then, so this is the initial condition, like this, this thing here is the initial condition. So basically, that should be known. I should know the initial condition of the current so that I can calculate the rest. So I will take this to the right-hand side. So let me fix this equation in this manner. So I will be just saying, so that was minus here, so it will be a plus here, right? So this is how my voltage current relationship will look like. So this is just the reverse of this equation. So we were saying Vt is L times di over dt, right? So now these two equations, by using these two equations, I can do the transitions from either from like current to voltage or from voltage to current very easily when I know, of course, the initial conditions. But of course, the initial condition only matters for this current equation. For the other equation, that if there is an initial condition, it will automatically drop due to time derivative. Like that constant initial condition will go away. But for this voltage to current calculation, you will need that initial condition. So it will matter a lot. You should be paying a lot of attention for those initial condition calculations, right? Again, in practice, people generally, let's say, chooses T0 to be 0. In that case, that lower bound will be 0. Like this lower bound will be 0. And then, of course, this thing will also be 0. So those two T0s will be equal to 0. But it depends on the application. Sometimes it's not really that case. Okay. Is there any question about this formulations, these equations we generated together? Anything you don't feel comfortable about calculating these components? Is this all clear for everyone? Can someone say something?
It's clear to me.
Okay, thank you. So that would be great if you respond and like some of you at least respond so that I can still know you exist there, because I don't see anyone and sometimes even like the connection drops, we can't even understand. So that is really helpful if you say something. Okay, so let's use these two equations on an example so that we can have some practice. So I will be writing an example here. So let's say, it says L is 2 Henries, again, remember the unit. And then it says Vt is 6 times 5 cosine, no, 6 times cosine 5t volts, basically. And then the question is, find IT if T0 is minus pi over 2, and then the initial current at T is equal to T0 is 1 amperes. Okay, so now the question is, we have the function, time-dependent function of voltage, and we are asked to calculate the current. So if you remember our beautiful equations, basically we will be using this equation. And then we are given the initial time, so that is great. We are giving the initial current value at that time, so that is great. I think we have all necessary parameters here to implement this function here, right? So I will be just plugging them in and calculating the result. It will be very fast and very simple actually. So let's pick another color so that you can see the solution. So we know our current is going to be 1 over L times integral from T0 basically that theta is minus pi over 2. I can just put it in here, right? And then that will go until t. And then here, Vy is 6 times cosine 5t, so that I will just put 6 times cosine 5y so that I don't confuse it with t. And then we will be having Vy dy. So I'm trying to remember the equation. And then we will say plus the current, the initial currents, which is 1 amperes. I know it already. So that is 1. And then actually I also know L, so I will be replacing this with 1 over 2, right? And then the rest is just calculating this integral. The rest is not really about circuit analysis, but of course, we are responsible for doing these calculations in exam. So I will be conducting the calculations so that we can find the results. So let's try to do this as fast as we can. So this is I of t. I can take the 6 out here. So that will be 6 over 2, which is 3 times minus pi over 2 to t cosine 5y dy plus 1. Okay, what is the integral of cosine 5y dy? So I need a volunteer to help me. What is this integral?
Sine 5y over 5.
Perfect. So that is sine 5y over 5. And then I need to evaluate this from minus pi over 2 to t, right? So I can take that 5 out. That is like, that will be 3 over 5. I think that will be just 0.6, right? And then for this inside, I will be having sine 5t minus sine minus what, 5 pi over 2, right? Please double check these calculations. Okay, I think that would be correct, but can someone calculate this part? What is, so that should be a constant number. It's just sine of something, and 5 pi over 2 is a number, right? So can someone calculate this number for me? What is sine minus 5 pi over 2?
Minus 0.1.
Minus 0.1? Are you sure?
Yeah.
Minus
Is that minus
0.1? Let me calculate. So this is 5 pi over 2. Sine is periodic over 2 pi. So this is equivalent to, so that is equivalent to, oops, sorry, that is equivalent to sine minus pi over 2, right? So sine is 0 at 0. At pi over 2, positive pi over 2, it's 1. So that should be minus 1, I believe, instead of minus 0.1. Can you double check this? I don't know who said this, but that would be great if you can double check. What I think is this should be equal to minus 1 instead of minus 0.1.
I used calculator.
Okay.
But you have to use it in Radimonds.
Yes, please. That is one thing extremely dangerous. And that will be failing you in exams. And really, believe me, no one in this department will be forgiving that simple mistake. You can say like, that's just a tiny
right.
bit of mistake.
You are
but
right.
Never do this mistake. Right? It's extremely critical. As engineers, the units matter a lot. Like the first thing I said about inductance was, if you remember, was like one of the first things we taught was like those units matter a lot, and no one really will forgive this in this department. It's this is extremely critical for your development. Okay, so now, do all of us agree on minus 1?
Yes.
Okay,
Yes.
perfect. Then let's do the rest of the calculations. So that should be now. So from here I have 0.6 times sine 5t, and then so that will be plus 1.6. So that will be like, I think 1.6 amperes, right? So now I think this is our solution. But please also don't just trust on my calculations, and of course your own calculations. Just double check those things, both for practice and to make sure that you make the right calculations. Okay. So this is how we can calculate the current given the voltage equation. It's if you really focus on what is going on here, it's most part of this is from your math class. It's basically math. We're just trying to use some equations that we again generate based on math, but we all started with this very fundamental equation right here. It all started with this equation here, right? So it's like when we know the relationship once, the rest is just applying math. So you should be extremely fast to gain time in your exams, especially. But you should also be very careful when doing those calculations, because those are not the parts of this course. But of course, you should be getting the right answer in your calculations. So you can just say, I made a unit mistake, and then now the building I did included less iron, like less stabilizing balances, and then that building collapses in the first earthquake, just like we are experiencing now. So this is not something we can't really make mistakes here. It's not possible for our applications. Also, like the things you will be doing later, again, will be very fundamental. I know, like most of our graduates work in defense industry. You can just say, like, we made a calculation mistake, and then the rocket we sent now hit the wrong plane. So that won't be acceptable for our job. So please pay special attention to the calculations part as well. Okay, I think this is a good time to give a small break, because we will start talking about powers, which I don't want to do in this very limited time. So let me stop screen share, pause recording for now, resume. Okay, so we were talking about inductors. We talked about voltage current relationship in both directions. So we learned how to calculate current and voltage given one of those two components. So that was very nice. Now we will be talking about energy calculations, basically the power and energy in inductors. That will be very similar also in capacitors. So once you learn those concepts in one of those components, it will be very easy to apply in the other one. So I will just say power and energy concepts, or just power and energy in inductors.
Hocam ekranı paylaşmayı unuttunuz.
Okay, thank you. That's. Let me do this. Okay, can you see now?
Evet hocam.
Okay, perfect. Sorry. Okay, so now we will be talking about power and energy in inductors, just to review again, since you are now able to see. So can someone remind me what power was, how we were calculating the power for a resistor, like for a resistive component? Do you remember the logic, like the intuition behind the calculation?
VI.
Exactly, yeah. So VI, so we were saying power was equal to voltage times current, right? That is actually the same thing here. It really doesn't change. We don't change anything. Like the power is for a component, the power is the voltage across the terminals of the component multiplied by the current passing through that component. So that is the very general definition of power. The only difference now is we now have a different relationship between current and voltage in this power calculation. Right? We may have only the current, or we may have only the voltage. So in those cases, we should be generating new power equations for us that just to make things useful. But of course, in any case, you know how to calculate voltage when you are given current, or you know how to calculate current when you are given voltage. So this equation will always be valid. But just for simplicity, I will be making some changes here. So for example, I will be saying, like, I know how to write V in terms of I for an inductor. So I can just generate one more equation for power. How I can represent voltage in terms of current? I can just say this is L times di over dt, right? So in this case, I can just say, so this will be basically, just to simplify, L times di times di over dt. So I can say this is also a power equation for an inductor. It's very simple. But also I can say, instead of plugging the voltage in, I can plug the current in terms of voltage. So I can say this will be V times for I will be using this equation we have here, so in terms of voltage. So that I can represent as 1 over L times this integral from T0 to T, right? Vy dy plus I T0. This is not really that important. You don't need to memorize these equations, but whenever you see them, you should understand where those things come from. Like, this is basically, both of these equations here comes from the same power equation you were using in resistive circuits. The only difference now is we have different relationship for current and voltage. Okay, so this is you can use any of those equations based on what you are given in the equation in the problem, right? So power, like if you think about the concept of energy in this case, so what was the relationship between power and energy? Can someone help me? Like, what is the
power
relationship?
was the time rate of change of energy.
Perfect. So we said power was the time rate, the rate of change in the energy, right? So this was the basic equation between the power and the energy. So this time now I can like, by using basically these equations, it really depends on the context, but I can use any of them. Like, let's say I will be just using this guy here. This I will be saying this will be equal to L times I times di over dt, so that I have now some common components here between this in this power calculation. So in this case, now if you focus on this part, both are divided by dt. I can simply cancel those over dt terms. So I will be having d omega equals to L times I times di, right? So this will be a very simple energy relationship. So in this case, I can just take the integral of both sides, and then I can calculate the energy stored in this inductor, right? So that will be very easy. Let me use a different color so that we can separate things up. So let's say we will be taking the integral. For the left-hand side, this is an integral with respect to d omega, like this energy. So that will start from the initial energy. I can just say maybe omega 0, which is generally 0, by the way. And then let's say, so that will be v of t, right? Omega of t, right? So it will be the power at any time. And then for the right-hand side, that is just an integral with respect to di. This L here does not depend on integration constant. I can just take it out. But for the bonds, I should say this is an integral which depends on di. So this lower bound will be I t0, and then this upper bound will be I of t, right? Is there any problem? But again, just not to confuse ourselves, I will be changing this parameters inside these integrals so that I can get rid of this. But also, I think just for clarity, we will be saying assume. So let's say let I t0 equals to 0. So there is no initial current in this inductor, which means that if there is no initial current, there cannot be any energy, so that V0 will be also 0. This is just an assumption for this case, but of course, this formulation here will allow us to solve this for a non-zero initial condition as well, so that is not a big problem for us. So I will be updating this equation. I will be saying this is from 0 to omega. So let's say this is just dx. I'm changing the variable name so that we're not confused. I will take that L out. So that will be from 0 to I of t, it doesn't matter. And then here we will be having y times dy. Again, I replaced i's with y's so that I don't confuse myself when I plug in those, i's back into this calculation. Okay, so what is the integral now? So this part, what is the integral of dx? It will be just x. So I will put that v in, so that will be for the left-hand side, I will be only having omega t, right? So what is the integral of y dy?
Y squared over 2.
Y squared over 2, so that will be 1 over 2 times y squared, right? And then I need to evaluate this at I and 0, and then of course I should multiply this with L. So let's try to do this calculation. So that will be omega t, which is the energy stored in an inductor, is equal to 1 over 2 times L times I squared. Because this, if I put this 0 in, that will be 0, it doesn't matter. So this is our energy calculation for an inductor. So this is energy stored in an inductor, right? And also, this is the power. This is generic for inductor, resistor, and capacitor. It really doesn't matter a lot, but now we have a simplified solution for the energy stored in an inductor. Basically, it will be 1 over 2 times inductance times the square root of the current, right? And the unit of this energy here will be again joules. What was the unit of power here? Unit
Watts.
of power? Exactly, that will be watts, right? Please be very careful, like pay special attention to units. Sometimes you will be giving like microjoules, millijoules, microamperes, like milliamperes. So you should be knowing how to convert those units to base units so that you can make things right in your calculation. So that is something very important. Okay, so let's do a simple example where we will be applying all these things, and then and then most of those things will be much more meaningful. So let's say we have an example here. I will be drawing a very simple circuit. So this circuit has a current source, which doesn't look in a good shape. I don't know why it automatically did this, but let's do this. We have an independent current source, which is just pumping current into an inductor here. Okay, so this inductor is, so let's say this is V, the voltage drop on this inductor, and this is 2 millihenries, where you should immediately, like there should be lights flashing in your mind, like whenever you see that milli, you should get that warning, right? We need a unit conversion. That will be 2 times 10 to the minus 3 henries. Right? Please, like whenever you see those kind of changes, just immediately you should have lights flashing in your mind, like warning message, so that you will be careful about the units. And then let's say this is IG, which is the current we are pumping into the system. And that IG is a function, basically. So that IG is 0 before t is equal to 0. So it's like we turn it on right at t is equal to 0. And then at after t is equal to 0, that would be 5 times e to the minus 200t minus 5 times e to the minus 800t amperes after t is equal to 0. So that is the that is just a graph. That is just a function of the current we are pumping in. And then now we have like this question has a lot of subparts, but let's do them one by one. I can't really follow. I won't be able to write them all and solve. So it says, what is the initial voltage at t is equal to 0? What is the initial voltage across terminals of that inductor? Is there any volunteer to help me? Volunteers? Can you hear me?
Yes, we can.
Okay, then we don't have a, okay, I will do this one. It's very simple. So we are asked to calculate the initial current initial voltage on the inductor. And we know the initial current we are pumping into that inductor, right? So what I should do is I will just calculate V of t, which is valid, by using which I can calculate voltage at any time. And then I will just calculate it at t is equal to t0, basically t is equal to 0, and you will get, hopefully we will get the result. So, so what I'm going to do is, let's see that equation as well. So we know Vt is L times EI over dt, right? So that is something we know. And then I will just put in the numbers. L is 2 millihenries, which is 2 times 10 to the minus 3 henries. And then what is di over dt? So this is I. After before t is equal to 0, I don't even need to calculate anything. It's just 0. But after t is equal to 0 here, what is the derivative of this thing? So I will just basically calculate the derivative here. So that will be minus, so then minus 2,200, no, minus 200 will be just a multiplication coefficient. So that will be minus 1,000 times minus 200t, I hope, right? If that is correct. And then we have this right-hand side where we have minus 5 times e to the minus 800t. So that will be plus 4,000, I think in this case. 4,000 times e to the 800t. Please double check my calculations. Does it look okay up to now?
Yes, I do.
Okay. And then now Vt is, I can just multiply everything with this coefficient here. So that will be, it's easier than I planned. So that will be just minus 2 times e to the minus 200t plus, is it going to be 8 times e to the minus 800t, right? So that is in the units of volts now. So now I have the equation for the voltage, and what I need is only the result of this at t is equal to 0. So what is V0? So that will be 1. So we will have minus 2 here, and then that will be 1. So that will be 8. So this will be 6 volts, right? This is the solution for the first part of this question. Okay, so the second part says, part B says, what is T star, let's say, when T star is 0? So basically it says, when does the voltage reach to 0? Do you all understand the question?
Infinity.
Atan, can you say again?
Infinity.
Why did you say infinity?
When it goes to infinity, the e to the power of t function goes to 0. So both of them will be 0.
Okay, but can there be other solutions, like other finite time solutions for this?
We can find it from the equation maybe.
Equation what?
Uh,
This one?
V of t, yeah.
Yes, so how do we find? So basically, let's say we have a given function. How do we find the time instant when it becomes 0? Like we are basically trying to calculate the zero crossing of the function. How do we do this?
Should we take
When
derivative?
the derivative, yeah.
Perfect. You take derivative of it, equate it to 0, and so that will give you the times like when is it asking 0 crossing? Yes. Yes. So you take its derivative, equate it to 0, just to find. No, wait a second. I think is there a problem with this question?
ln4 over 600.
I will just try to. Okay, sorry, we don't need to take derivative. Yeah. Let me just look at the solution, just to read the solution. Calculate the time instant when voltage reaches 0. Okay, sorry. This is my mistake. We don't really need to go ahead and take the derivative. It's when you're trying to calculate the maximum or minimum values, right? So whenever you want to find local maximums or local minimums, or like global ones, it doesn't matter. You take derivative and equate to 0. But this question is simpler than we thought. It's just asking when this equation becomes 0. So basically, I will just equate it to 0, right? So I will say V t star plus 8 times e to the minus 800 t star is equal to 0. So I just need to calculate that t star. Is it? I think that should be the answer, and we can calculate. We can compare our results with the results I have here. Is it clear for everyone? Like it's not asking the maximum or minimum, the time of maximum or minimum. It's just asking the time when it becomes 0. So I can just equate it to 0 and calculate that time very easily. So here I can take this to the right hand side. So that will be like 8 times e to the minus 800 t star is equal to 2 times e to the minus 200 t star, right? And then that will be just 4. So if I divide both sides with e to the minus 200 t star, so that will be something like this, I hope. So that will be 1 over 4. Is this going okay up to now?
Yeah, I think so.
Yes.
Okay. So then this division will be just a subtraction of the power. So that will be e to the minus 600 t star, which is equal to 0.25, right? So that is just how we go. And then to calculate t star, I need to calculate ln of these numbers, right? So that will be, if I take ln of both sides, so this left-hand side will be minus 600 times t star. And then this right-hand side will be ln of 0.25, which you should calculate. Can someone calculate this number? And then t star is just ln of 0.25 divided by minus 600. And this should be a negative number, like this ln of 0.25, so that we get a positive time. Can someone calculate this number for us?
Minus 1.38.
Which one? This one?
39.
39? This ln or everything?
Yes.
Only ln.
Okay, can you also divide it by 600? So that we can find the time instant?
Minus 2.31.
What, seconds? It can't be because this is 600.
Over thousands.
Over 1,000?
Yeah.
if it's over 1,000, then I will just say this is milliseconds, right?
Yeah.
Okay, so can
It
you?
should be
This
positive.
should be, yeah, this should be positive, exactly. Because this is negative, the result will be positive. Please double check this result. I don't have the complete solution here, so it's not easy for me to check, but I just believe in those numbers. Please double check, and then let me see the part C of this question. Alperen says, I agree, and then Emrah says, I think the same result. Okay, I think we found the correct result. And then
Yeah, there's no issue.
okay, perfect. And then part C says, let's focus on part C. Part C says, what is the power on 2 power of t, let's say, on this 2 millihenry inductor? So basically, we need to calculate the power here. Again, it's extremely simple for us now. We will just multiply voltage equation with the current equation. We have the current equation. We have the voltage equation. We have everything. It will be very simple for us. So let's say power on this 2 millihenry component is just 3 times R. And then again, I can just say, what information we have? We have IG directly. I can just use it. And then what else we have? We have voltage. We calculated the voltage, right? Yep. That should be very easy. So this is the voltage equation. But well, someone should remind me the solution. Or let me see if I can do this.
At the top now, voltage equation.
No, like when I go here, I should remember that equation. So this is, I will say, just paste if I can do this easily. This was our voltage equation, right? I just copied and pasted, and then our current equation is 5 times a lot of things. So 5 times e to the 200, 5 times e to the 800. So I just need to remember it. 5 times e to the minus 200t minus 5 times e to the minus 800t. Can you double check? I don't want to make a mistake here. And then I just go ahead and do the rest of the calculations. I will just do the multiplication. So that will be minus 10 times e to the minus 400t plus 10 times e to the minus 1000t, I believe. And then plus 40 times e to the minus 1000t minus 40 times e to the minus 1600t, hopefully. And then what I can do, so these are the same thing. So this will be just 50 times e to the minus 1000t, right? I don't know if there is any further simplification I can make. So that will be just the power here will be minus 10 times e to the minus 400t plus 50 times e to the minus 1000t minus 40 times e to the minus 1600t, and the unit will be here again, watts, and this is valid after t is equal to 0. So this is our power equation. Do we all agree with this? Do you all agree with this?
Yes.
Yes.
Okay.
In previous
So-
step, sir, sorry. In
Sorry,
previous
can you
step-
say again?
in previous step, minus 40 times e to the minus 1600t. It's wrong.
Which one? This one? This one?
I can't see. So, yes, e to the
Let me see.
minus 16,000t.
1000? Okay. Wait a second. So you're saying no. Wait a second. Like we are multiplying this term with this term, right? So 8 times minus 5 is minus 40. And then both have powers minus 800 and minus 800. I just
Oh, sorry,
sum
my
them up.
mistake. My mistake. Sorry.
Okay, perfect. Okay, no problem. So, okay, now since we agreed, I will be continuing on this one. So the next part of this question says, calculate the time instance. So let's try to write it here. Calculate the time instance, calculate T star again. I will just say T bar, just to simplify, for maximum power. For maximum power. So okay, so now we have the previous case that we skipped last time. So now we have the power equation. We need to calculate the time instant when we have the maximum power on this inductor. So how do we do this now? We already gave the answer before.
Take the first derivative, find the point at 0, and then check if it's a maximum or a minimum.
Perfect. So this is exactly the steps we should take. So we will just take the derivative of this P we calculated before, and then we will equate it to 0. We may have multiple solutions. We will check if they are maximums, minimums, and we will pick the maximum one, and we will say, okay, that time instant is when you have the maximum power, right? So let's take the derivative as fast as we can. So dp over dt is, now let's take the derivative. So that will be plus 4,000, I believe. Right? And then the next one will be minus 50,000 times e to the minus 1000t, and then plus 64,000, right? E to the minus t, and then we will equate this to 0. Okay, so since we are equating to 0, I will try to find some common terms that I can play with. So what common terms I can factor out? So for example, I can directly get rid of this term by extracting this term from the other guys. So I will just say maybe 4,000 times e to the minus 400t. In parentheses, I will be having 1. Oops. 1. So for this one, if you divide 50,000 with 4,000, you will be having 12.5, I think, right? And then if I subtract minus 400 here, so that will be just minus 600. And then for this one, if you divide this with 4,000, you should be having 16,000. No, just 16, right? We agree with this? Please double check these calculations. This should be now 1200. Is this clear for everyone? So I just factored out this 4,000 times e to the minus 400t out, so that I now have multiplication, because I'm trying to equate this thing to 0. It will be difficult to solve this problem by directly trying to solve this thing. That is very difficult. Is this okay for everyone? This current step?
Yes.
Okay. Can you use a calculator instead? Yes, exactly, Aaron. We can use a calculator at some point. Maybe this is a nice point, but we need to simplify these things a little bit more so that it's meaningful to use a calculator. So otherwise, you will be getting a lot of roots that we don't even understand. So here, if you look at this multiplication, this part can never be 0, right? Unless you are going to infinity, right? In a finite time, this thing cannot be 0, this left one. So if this equation is 0, that 0 will be due to this term. So this term should be equal to 0 at some finite t numbers, right? So here, just for simplification, I will say, for example, let x be e to the minus 600t, so that I can simplify these this equation further. So in this case, I will be saying 1 minus 12.5x plus 16 times, like since this is square of this term, so that will be x squared equals to 0. I think now it's a good time to use a calculator. So Aaron, did you calculate this? Did you find the roots? Okay, Aaron says something. Give me a second. So Aaron says T, one possible T, he says, is 4.8 seconds. Can you double check these results? How did you find this? Or wait a second, did you mean this for X or T? Okay, I need a volunteer. Fatih Çelik says a different number. Okay, everyone says different numbers. Actually, we should be having two solutions here. Okay, what is that? Etembura writes 0.69 and 0.09. Are those for X or T?
X.
Okay, okay, let me write these so that we can move on. So for X, you say one possible solution is 0.09, and then the other possible solution is 0.69. Okay, so this is our X. So what is T in this case? So that T will be, should be ln of that number, right? Divided by 600, minus 600. So ln of 0.09 divided by minus 600, and then T2 should be, based on this calculation, T2 should be ln of this number divided by minus 600. And now I need these numbers, T1 and T2. Can you calculate these, T1 and T2?
T1 is 4 millisecond.
4 milliseconds.
Yes.
Okay, T2? Someone says something. T1 is
680 microseconds.
618 microseconds. Wait a second. I will just say US, like that U is micro, or I can just say micro S. Okay, so these are two time instants where this power equation, the derivative of this power will be 0. But in order to know which one is minimum, which one is maximum, we should put those numbers back into this equation and calculate the power, right? So we have one more step. So let's take this equation. And again, I will need your calculations. So let's copy this. So now, please use your calculators and tell me what P1 is, what P2 is. So let's say P at T1, and then we will have P at T2, and then we will compare. Is there anyone who can calculate them, or are you calculating? I don't know. Are you calculating this, or should I do this? Okay, can you hear me?
Yeah, I'm calculating.
Okay, okay. Also, if any other person is calculating, please write your results to chat for PT1 and PT2 so that we compare them and decide which one is max. Anyone else?
For PT1,
Okay.
minus 1.17.
What?
Yes.
Okay.
watts.
So definitely that is the minimum. I mean, at least we have zero energy at t is equal to 0. So this T2 should be the correct case, but did you also calculate power at T2?
It's 4.3 watts.
4.3 watts, thank you. So as you can clearly see now, we can say maximum power occurs at T equals 618 microseconds, right? So this is the time. Thank you everyone for helping me. So let's see the next problem here. So it says, what is the maximum power on the inductor? Which is we already calculated. Okay, so the response to that next one is this. Like we know the maximum power occurs in this time instant, and basically maximum of P2 millihenries will be 4.3 watts, right? Okay, that is already done. The next sub question says, okay, this is nice. What is the T when energy is maximum? Okay, this is very nice. And then it also asks for the maximum energy. So we need to calculate both. So we will be calculating the time instant when the energy is maximum, right? So if you remember, I don't know if we calculated the energy before. Did we calculate the energy? No. Okay, we will do it now. So, so we all remember what the energy calculation was for an inductor. We were saying energy is 1/2 times L times I squared, right? So in order to find the maximum, we will take the derivative of this with respect to 0, and then we will we will find the time instance, and then we will calculate this this thing. But we can make some intuitional comments here. First of all, so we will be, let's say we will be taking derivative of this and equate to 0. So this will be a T star here. But actually, it is the case. So this is 1/2 times Li squared. This is equal to the time instant when you have di/dt is equal to 0, right? So it's like when you have the maximum current, you will have the maximum energy. Is this okay for everyone? Is this clear? Like we are trying to calculate the time instant when we have the maximum energy. And I am saying, based on this equation here we have the maximum energy when we have the maximum current, because this is just a constant. So whenever this thing becomes maximum, we have the maximum energy. So I can just, instead of taking the derivative of that huge equation, which includes I can just take the derivative of this I and calculate calculate its calculate when its derivative will be equal to 0, right? Is this okay for everyone? This is really important.
It's clear to me.
Okay, perfect. So when do you get this thing equal to 0 then? So the next question is, can we try to intuitionally understand what happens when di/dt is 0? So if you remember the voltage equation, voltage is L times di/dt, right? So we are looking for the instant when this thing is equal to 0. Basically, we are looking for T star when voltage is equal to 0, right? So if you follow the steps carefully, we are trying to find when energy is maximum, which is when the current is maximum. In order to find when the current is maximum, we will take its derivative and equate it to 0. But when current derivative of current is 0, we know it is the time when the voltage is 0. And if you remember, just going back somewhere, I think here, we already calculated this time instant. So we know when voltage is 0. It is at t star equal 2.331 milliseconds. So I can immediately say this t star here is same as the one we calculated in part B. And I think this the only purpose of this question, like we did those steps, so now we are building on those solutions. So this is when t star is 2.31 milliseconds. Now, for the last part, I need to calculate the energy in this time instant. So that will be 331 times 10 to the minus 3, right? So I need to calculate 1/2 times, what was L, our inductance?
2 millihenries.
Okay, 2 millihenries. So this will be 2 times 10 to the minus 3. And then I will be calculating the I square. So I 2 10 to the minus 3. So I will be taking the square root of this, right? So that will be my answer. And we need to do this calculation. So we have the current equation. I can directly put this number back into that equation, right? So we have the current equation somewhere. Maybe, okay, like far at the beginning. So is there any volunteer to calculate this? So we need to use 231 times 10 to the minus 3 instead of this t and calculate the current value here. This is the last thing we will be doing for today. So if you can finish this, we will be having all like numerical solutions for everything we did today. By the way, is there anyone who is calculating, or should I calculate?
I'm calculating the current.
Perfect, thank you. So if you can give us the number, then we will also calculate the energy after this step, so that these 2's will cancel. So this will be 10 to the minus 3 times the square of that current, whatever we get from, I think it was calculating.
Yeah, it's 2.36 amps. So squaring that, it would be 5.58 amps squared. And it's going to be, with 10 over minus 3, it's going to be millijoules.
Okay, 558 you said? This will
Yes.
be millijoules. Okay, perfect. Thank you very much. So this is our result here. So our result. Okay, so now we also calculated the energy. So it's like for this type of questions, we are trying to calculate almost everything. Like we are solving almost all possible questions, like energies, maximum, the times when you have the maximum energy, time when you have the maximum power. So all those things are like all summed up together. So that is a very nice question that I would really suggest you to work on this one more time, just to do the calculations yourself so that you can practice this again and again. So we can say, now this is okay for everyone in this class. Like you all understood this, this very well. Okay, let me stop recording.